welcome everyone. We're just going to give it a minute as folks are still joining in. I have this tendency of making like this into a podcast live with Chris Harrison from Chris's Place. So give it just a moment. We're just letting folks in both into the Zoom room, and you can also probably watch us over the live stream on YouTube. If you're in any of the platforms, after Chris's talk, you can ask questions. On Zoom, you should be able to see a Q&A feature, or you can type them in the chat and we're able to read them out, and I'll read the questions out and relay them to Chris. You can raise your hand as well if you're on Zoom. If you're on YouTube, one of us will go and grab the questions from the YouTube chat and pass them over to here. So feel free to also ask questions if you're watching us from the YouTube platform. So let's just wait 2-3 more minutes. Give folks a chance to come in.
Tom, could you post the live stream link on the chat? I think someone was asking about registration again.
Certainly, just a moment.
All right, I think this is a good point to start. We have about 35 on one side and 20-something on the other side. So, more folks will join us in certainly as we start. But I just want to give it a brief introduction. This is also the first time we're hosting one of these distinguished lecture series in human-computer interaction. They'll be running throughout the fall, and I want to welcome you all very warmly to the University of Chicago, although virtually, because you're actually seeing my place and Chris's place on your screen. But just to tell you that we're kickstarting this series, and we have a really exciting set of speakers for you coming over. And I hope you can join us for all these talks that you see right now. Today, I'm especially happy that you were able to join us for Chris's talk, the very first one. Also, a shout out to if you're a student at the University of Chicago. We're doing a lot of activities to try to join us together in these more remote times. And one of them is the HCI Club. So if you're a student in Chicago and you haven't joined for one of these fun informal meetings that Blaze, Marshni, and a bunch of other HCI faculty, myself, host, feel free to join us. The link is on your screen, and you'll be able to find it as well on the Zoom chat. So I want to introduce Chris, who's our first speaker. And, I could say a million words about Chris, and I'll try to make it as brief as possible so we can get to actually hearing from his work. Chris is an associate professor of human-computer interaction at Carnegie Mellon University. His work investigates novel sensing and in broad sensing on interaction technologies as well. Chris has been named pretty much everything that is important in recognition. Top 30 scientist by Forbes, top 35 innovator by MIT Technology Review, and he's gathered so many other recognitions. So rather than turning this into a very long list of achievements from Chris, which you can read online in his webpage, and it's truly amazing. I also just wanted to tell you a personal story of how I think Chris's work is very influential for HCI researchers like myself. When I was a master's student, I was just taking my first HCI class, and I was starting to read HCI papers. I started to gather some personalities in the field that I thought were really inspirational, and that list included folks like Joe Paradiso from MIT and Hiroshi Ishii from MIT, who we luckily also have in this series. But these are very established folks. But there was one person in my list of complete inspirations that I always looked up to, and that he was a PhD student at the time, and that gave it an extra inspirational vibe to it. And that was Chris. So Chris's work was one of the first that kind of blew my mind. And I think even by the time Chris was a PhD student, he was already really shaking the field of HCI. At the time, especially, I think, saying like, hey, everything can be a sensor, and look at how you can transform objects around you in becoming a sensor. And I'm sure in these truly responsive environments talk, we'll hear more about that. But I think that's just a small piece of what Chris has contributed to the field. And he's been on par with names even before, he was a professor at CMU And so I'm really, really, really proud to have Chris over here, sort of 10 years later, to tell us all the things he's done since then. And without further ado, I want to introduce Chris as our first speaker of the series. Chris, feel free to share your screen, and let's hear it from you.
Well, thank you for that very kind introduction, Pedro. Your work likewise inspires me today, so you're paying it back the other way now. Hopefully, you can all see my screen. I'll try to keep my eye on chats, but please definitely feel free to interrupt me if there's a short question. But if not, we'll tackle those at the end. So today we're going to talk about this notion of truly responsive environments and how we might get there. There's a long way to go, unfortunately, but I'm hopefully going to give you a little bit of taste of where we have to go. A little bit more background on me. So I am an associate professor at the School of Computer Science at CMU. And inside of that, it's a very large organization. There's an actual department of HCI. And inside of that, I run a group called the Future Interfaces Group. And you can pull up more details on that webpage. And the lab draws on several strengths. Most notably, we like to play with sensors and signal processing, and we combine that with machine learning and computer vision techniques to make sense of those rich signals. And more uniquely, although not compared to someone like Pedro, is that we don't just play in software. We actually do a lot of physical prototyping because computers inherently live in the world, and they have to be embodied in the world and used by humans. And so we kind of take these three kind of thrusts, and we try to build entirely new computing experiences with them. And in terms of sort of an ethos of the lab, we often kind of approach problem domains in human-computer interaction by asking, what are the computational ingredients that we might be missing that could allow us to bake essentially whole new computing experiences, or at least improved versions of current experiences. And it often takes a lot of ingredients to bake something like a cake. And so in my lab, we're often drawing on advances from other fields, whether that be NLP or computer vision or cloud compute or sensors or so on, to make breakthroughs. But we're always have this lens of, what's that missing ingredient to bake this incredibly delicious thing? And we go about and attack those problems to unlock those ingredients. The other thing that we do a lot is we look at historical trends, which seems a bit odd maybe for a computer scientist that tends to be looking in the future. But I like to look along trajectories in computing to see where we might be going. And there's a lot of really interesting trends to draw upon. And so in today's talk, I'm just going to share one of those trends with you today. And I'm going to start my lecture or my presentation here with a very short clip of Professor Koons describing Ivan Sutherland's Sketchpad system. Now, if you're unfamiliar with Sketchpad, it's not critical to know. Instead, I really want you just to listen to what he's saying about computing of the past and computing of the future. But keep in mind, this is the 1960s.
But little by little, he will begin to investigate ideas, and the computer and he will be in cooperation, in the fullest cooperation in this work.
Well, now, how is this different from the way the computer has been used in the past to solve problems?
Well, the conventional way, the old way of solving problems with the computer, has been to understand the problem very, very well indeed, and moreover to know at the very outset just exactly what steps are necessary to solve the problem. And so the computer has been, in a sense, nothing but a very elaborate calculating machine. But now we're making the computer be more like almost like a human assistant. Okay,
so there's a lot of really awesome quotes, even in that very small snippet, but I want to talk about just two. So first off, Professor Koons kind of pokes fun at the old way of solving problems, right? And that is, in order to use a computer, you have to understand the problem really well. You have to know at the very outset what the steps are going to be to solve the problem. And this is essentially how we still use computers today. We are using them as tools to get things done. If you want to, look up a recipe of how to make French toast, you know where to go, you know what to do. It's actually fairly mechanical. And most of the tasks we're doing on computers today are fairly mechanical. And it's not that different from how you might go and build a house or even something creative like, painting art. It's a process that you go through with a set of tools. But the second quote here is something that is hinting, I think, at something much deeper. And that is that the computer and the user will be in the fullest cooperation. And that's not how you describe a tool, right? You don't cooperate with a hammer or cooperate with a paintbrush. But these folks, even back in the 1960s, when computers were obviously very rudimentary, they were thinking of a computer as something much, much more like a human assistant. And I actually, later in this video, but I didn't include it here, they actually describe computers as a coherent partner in the task that you're performing. I think that's a really wonderful, wonderful term. And so I think we're very much stuck in this kind of computing as a tool era. Even now, 50 years later, half century after that video I just showed you, we still are really using computers as tools. And we're nowhere near this very intriguing and wonderful idea of having a coherent partner, that our computer as a partner in tasks that we're performing. So with that setup, let me actually return to my earlier question. What ingredients might we be missing to enable this future as computers, as partners? And I think a really important ingredient is context awareness. So for those of you who are not familiar with this term, put very simply, it's really to just be aware of one's surroundings, both physical context and social context. And you'll be very fortunate that the next person to present in this seminar series is Nin Day, and he's really one of the very earliest people to explore context sensing, and hopefully his presentation will touch on that. So what are some examples of context, just to kind of set the stage here? So you might have, for example, a student that is at home focusing very hard to finish an assignment, a business person in an office trying to close an important deal, a really angry or frustrated driver, and a family dinner. And these are all very different physical spaces with varying constraints, and they're also very different social settings as well. And so I would ask you, right, if you personally had a dedicated human assistant, would they act or react differently across these different contexts? And of course they would, right? They might get a piece of news, but decide to withhold that until you finish your homework because it's not super critical. Or if it's related to that dinner, perhaps there's a guest that's running late or the food is burning in the oven, is they might decide to intrude because it's highly relevant and important. And that's really the power of a human assistant that's making that judgment call. But unfortunately, today's computers are really super far away from context aware. In fact, I would argue they're really context dumb. And for that reason, they're not very good assistants. They're great tools. Now, don't get me wrong, computers are fantastic tools, but right now they're terribly bad assistants. They tend to distract and interrupt us rather than really keeping us focused. And the idea of a computer intruding to proactively help us when we might be going down a wrong path is essentially science fiction, right? They really know almost nothing about the immediate world around them. They don't know that you're having dinner. They don't know if the dinner is burning. So how can they possibly be context aware? So I think it's kind of crazy to think that, these supposedly smart speakers, the ones that are sitting on your kitchen countertop, they may have no idea that they're in a kitchen, let alone that you're making dinner, right? Despite having all these really sophisticated sensors and cloud compute at their disposal. And we can also think about, smartwatches, right? They'll happily recite to you the full history of Australia and tell you the real-time traffic conditions in Sydney, and yet they know nothing about your hand that's just 10 centimeters away, right? So there's clearly a breakdown. We're missing something here. So I think we've got a lot of work ahead of us to achieve this vision of computing as partners. And we need a bootstrap computer starting at the very bottom with new approaches for computers to sense their surroundings, on top of which we can build models of context awareness. And if we're successful, those will be the crucial ingredients that help us unlock that future of computers as partners. So, with that set up, I'm going to tell you a little bit about some of the research that my lab has been working on in this area. And I'm not going to go into too much depth on any single project because I want to purposely show you breadth, but we can certainly dig into it more in questions. So first off, I want to talk about synthetic sensors. This is actually a fairly old project in my lab, started back in 2016, and it's continuing to this day. And it's this notion of synthetic sensors, which is now actually becoming a practice that's being adopted in industry. What we did first is we surveyed all of these kind of IoT sensor boards out there, these little tiny boards that are populated with sensors. And we looked at both academic and commercial systems. And we looked at what type of sensors they were including on their boards. And what we did is we said, we're just going to take all of them. Maybe there's a board that's environmental focused, that has barometer and humidity and temperature. And we said, okay, we're going to take all of those, and we're going to do one that's an industrial sensor, and we're just going to smash them all together and make sort of a super sensor. And we're going to take everything except the camera, because we know that that is a significant non-starter for many people. So it's everything but the camera. And we packaged that together into what at the time was the most sophisticated sensor board out there. And even today, actually, it still has more sensor capability and compute as well than most commercial offerings. And so here's what that board looks like. And you just basically plug it into wall power. Now you might be wondering, where's the battery here? Why use wall power? And this was a very purposeful choice. We wanted to sidestep this enormous issue of having users have to go around and replace all the batteries every few months. In our initial work on this project, we found that a typical house has something around 100 facets that would be useful to monitor. Is the coffee machine on? Is the laundry machine on? Is the stove on? Is the HVAC running? Is your basement flooding? If you kind of total up all the things that you might want Alexa, let's say, to know about in your home, it's around 100 different facets. And that would mean replacing 100 batteries a few times a year. And that is also a consumer non-starter. So we decided to go with wall power to just eliminate the power issue entirely. But this comes with a downside. Because we're not physically attached to the object that we wish to sense, and we're not physically attaching the sensor to the coffee machine or the laundry machine or whatever it might be, we have to be much more clever with our sensing. And so this is when we do sort of an extreme sensor fusion plus AI approach. If we do that, we can actually sense a wide variety of activities from a distance. So here you can see one of my we're going around and turning on various things in this cube. The laptop is showing you the signals and also the live classification. So importantly is that instead of one sensor per object, we're now getting it down to one sensor per room. And that makes it much, much more practical. So here's just a quick reel here. Again, that sensor's plugged into the outlet between the mirror center. It's also showing you the kind of breadth of activities that you might want to sense even in just a single house. It's been on for a while, but so those are all basic activations, faucet on, faucet off. Those alone aren't that powerful. So we tend to call those first order synthetic sensors. They're the binary activations. But what you want to build on top of those binary activations are kind of second order synthetic sensors, these higher order sensor streams that are built up from lower order events. And these typically track things like rate or count or state. So here's an example, a second order sensor. It's taking the feed of, I just heard a towel come out of this towel dispenser, and a second order sensor is keeping track of count. So it's one higher level kind of up in sort of knowledge. Likewise, we have a flow rate sensor, but we don't have something to accumulate it. So a second order sensor might be have a usage of water for maybe an entire home. And that could power things like on social media and so on for sustainability. But what's more interesting is that you start building up higher and higher and higher. So now you take the, the flow rate sensor and the, noise sensor, and is this drawer open sensor, and now you start to piece together that things like the family's eating dinner or Chris is busy right now. And then those slowly become the ingredients to start building that really kind of awesome cake, which is going to be this full kind of context awareness. And so we kind of want to keep on building up these sophistication of these sensors. And what's also really cool, and why this project is still alive and well, is that we've deployed it. We've deployed these sensors to a lot of industry partners, and they're also increasingly being used at CMU. And so this is just one example of that. Professor Agarwal, also at CMU, he led an effort to install 350 sensors, pretty much every room in this new building that's under construction at CMU, and which is going to open shortly. And so now we have this incredible test bed, this really rich set of sensor data. On average, I think there's 2 sensors per room to really have a kind of a full exploration of what it means to have a truly sensed environment to power some of these end user applications. Now, in the synthetic sensors paper, one of the, I think, the most interesting things that we did from sort of an academic standpoint is we rank ordered all of the sensor channels by their relative information power. So, how useful is a barometer in the home? How useful is an accelerometer? And what we found is that the microphone, sound, is really the most useful. It's not that it's the only one. You can't get away with only the microphone for some things, but in many cases, the microphone is really capturing, 60 to 70% of the activities in a room. And it underscored really the utility of sound for context awareness. So what I'm going to do on my next slide to sort of set the mood is a little bit of a test. You can close your eyes if you want, and I want you to try to guess the activity. So just listen to the sound and guess where they're going on. Not only maybe what's going on, but maybe even what room. So try it out. So what you would have found, and I don't know how the audio is over Zoom, but humans can be around 90% accurate. They can tell that you started up a vacuum, or that you're sort of mixing something in like a cereal bowl, or that you're brushing your teeth. And if you had eyes open while I played that video, you would have seen that in each of these scenarios, there was a computer with a microphone nearby. So in this example that's up right now, someone is brushing their teeth. And of course, there's a smartwatch with a microphone sitting right there on the wrist, not 20, 30 centimeters away. And so what we did in Ubiacoustics, with that kind of very simple insight, is try to build a framework and a process that allowed people to essentially just drag and drop what they wanted these devices to know about what's happening in their environment. So in this case, this is an Alexa, it might be sitting in a kitchen, and we can literally just say, we want you to know about the doorbell, the dishwasher, the blender, chopping, to give it this kind of, afford it this ability to do this context awareness. So if you want to know when your dishwasher's done, you can just drag it over. And more uniquely in this project is to train this deep learning model is we leverage professional Hollywood sound effect libraries. So CMU has some great licenses at the university because of its film program. And as far as we know, we were the first group to leverage this as a sound source for training. And boy, oh boy, was it a total bonanza of really well-structured, clean data that led us to all sorts of really interesting data augmentation. So we could train our models essentially for free just by doing a query in one of these professional databases. And so you could do lots of things with just sound. So one of the things we did was with smartwatches is listen to people that are coughing nearby, or ideally you. And if we see an uptick, we can actually proactively go in and say, hey, you're coughing a lot. Do you want to schedule an appointment? And sort of more of an industrial kind of workshopping kind of case, listen to sounds that are happening and automatically keep sort of a maintenance schedule. So how many of these things have been running for how long, and when do things maybe need service? And then this is a very simple last example, but I think it's illustrative. The smartphone wakes up from sleep and says, don't forget to wear your shirt. And because it knows further that we're using a drill press, it actually figures out using its own kind of regression model that we're running at a particular RPM and what that RPM might be good with. So it's good for softwood, and maybe you're drilling out a piece of hardwood and you might adjust your behavior. So it's automatically sensing, automatically stepping in to ideally change the user's behavior or make them more effective at their job. So most recently, we've been kind of continuing along this. This was published this year. We've been trying to think about how do you avoid this bootstrapping issue. The problem with training on Hollywood sound effects is they're a fantastically good data source, but of course it's harder to kind of model the reverb in an environment. Different appliances sound different. So your blender, sounds different from my blender. It sounds different against your backsplash than it does against my backsplash. And so even though these sound effect libraries might contain 1,000 blender sounds, which is not actually uncommon in these libraries, they still aren't as good as the real thing, which is your blender in your kitchen. But at the same time, we don't want to have to train systems where you have to go to your kitchen and turn on every single thing and say, this is my blender, this is the door, this is the left door, this is my refrigerator, because that's also very cumbersome to the user. So we thought about sort of this compromise approach where a device like an Alexa or a HomePod can sit in your kitchen and just listen passively. And once it's sort of built up enough data, it knows that there is a distinct object. Only then does it interrupt you and say, can you tell me what that is? And you'll say, oh, that's a faucet running. And then it can actually leverage maybe the 100 hours of recordings of your faucet. It's already kind of clustered and stored. And now it has enough to bootstrap a deep learning classifier. So here's just a very simple example. There's a Apple HomePod sitting on the counter. And we have Jason Wu at CMU, he's chopping. And you'll see it sort of dropping these dots down because it's clustering those sounds. This is a very low dimensional projection of the sound space. Cutlery sounds very different, and so it actually gets projected sort of into a different spot. And then over time, this is just 5 minutes or something, but you can imagine over the course of the first week you might own a device, it sort of builds up this big cloud of all these known things. Eventually,
what was that sound?
That was a microwave.
That cluster that's on the left there is sufficiently far enough away and sufficiently distinct that it actually interrupts to ask for it. And now you get a label for all of those dots. And of course, this process can continue for weeks and days, and eventually you actually get clusters for everything. So this is a way to avoid that bootstrapping. Basically, you get one question. And of course, there are sort of fleet effects, from people deploying it across many different homes. But this one is heavily tailored, has the benefit of being heavily tailored to your home and yet very low intrusiveness. So the other kind of issue to discuss here is that deployed sensors are going to always have limitations, because you have to anywhere you want coverage, you have to deploy them. And of course, if you go to someone else's space, like you visit someone else's home, are they going to grant you access to their kind of sensor data in order to bootstrap this context awareness? So there's some really kind of tough, not only kind of data sharing and privacy issues, but just kind of practicality issues at large are significant. So the other approach here is to attempt to be entirely self-contained and have the user wear everything that they might need to sense context. So for example, you might put all the smarts in the smartwatch, and that would make it far more practical, because then environments don't have to be instrumented at all. You can just walk in and yet gain this context awareness. So let me just give you some quick examples here. First project is Msense. And this takes advantage of a very simple property, and that is that electrical and electronic devices, when you run them, they actually emit a little bit of RF noise, electromagnetic interference. And so in essence, you can think of them like very weak radio stations. And so when you touch these devices, when you're using them, like in this case, like a sander, your body becomes an antenna for those signals. And if we place a sensor on the user's skin, we can actually detect these sensors and figure out what object or what device a user is touching. So here's just a very quick reel of these different devices. And what you're seeing on the laptop screen there is basically an FFT. It's a frequency plot of the different characteristic frequencies that we're seeing from about 0 to 2 megahertz. And those are characteristic enough, it actually lets us recognize what object the user is touching, as you can see there at the bottom of the laptop screen. And of course, what a user is grabbing, what is on and they are manipulating, is obviously a really important piece of context. So there's lots of things you can do here. Obviously, if you're brushing your teeth, you might automatically have your smartwatch start a timer for 60 seconds because that's good hygiene. If you step on one of these weighing scales that does BMI, there's an electromagnetic interference that kind of runs through your body again, and we can automatically launch sort of your weight history for the past month, let's say. So it's automatically, proactively launching applications that might have relevant data that you want to look at. And same, we can build up, for example, you touch the refrigerator, you touch the stove, it's 8:30 in the morning, perhaps you're making breakfast, do you want to play NPR or something like that? So again, you're starting to build these kind of building blocks together. Now, Msense was very cool and actually surprisingly accurate, but it did require a new sensor to be added to smartwatches, which made it much less practical to deploy en masse. It also couldn't detect non-electrical devices, so like scissors or chopping vegetables with a knife. Those don't have any, they're not electrically powered, and so we missed those events. And so in follow-on work, we turned to accelerometers as our sensor of choice because they're already found in smartwatches. So if we could get this working, we can actually basically deploy this to all smartwatches that are out there already. And so this is what we did in Viband, is we went in and kind of hacked the Android kernel on this Android smartwatch, and we replaced the default accelerometer driver with our own version, which allowed us to receive high-speed accelerometer data. So instead of 100 hertz, which you might typically find on a smartphone or watch, is now we have it at 4,000 hertz. And at this sample rate, you start to see some really interesting and characteristic mechanical oscillations. So what you're seeing here in this video is the top signal on that laptop. You see it's very kind of coarse line. That's a typical 100 hertz accelerometer. And you'll see when we pick up this mechanical toothbrush, you don't really see any kind of sinusoids because it's way too low frequency. The oscillation of this brush is way higher. But on the next line down, the accelerometer running at 4,000 hertz, you can actually see this very characteristic oscillation of the motor inside that toothbrush. And of course, that is going to reveal that particular toothbrush. So this turns out to work across a whole range of objects, so instruments and vacuum cleaners and drills and toys and so on. And it allows us, again, in a very similar way to Msense, to recognize what tool the user is working, and it doesn't even have to be something that's electrically powered anymore. And of course, this can be around for a while. So just a quick example here, you might be kind of baking a cake and your iPad now has a little bit more context. And so it'll say, keep mixing, it'll show you a progress bar. And if you stop, the progress bar will stop because it's known you stop mixing, and then you can resume again. So again, we were really intrigued by this idea. It was kind of convinced us as a research group there was still amazing opportunities to be squeezed out of existing hardware. I mean, who would have thought that the existing accelerometers on these watches could do this? And so we doubled down on this approach of using an accelerometer, and we attacked the problem again last year. And this time we wanted to get a lot more real world data. In Viband, we mostly collected this data in the lab, but this time we really wanted to get out and get real world data. And so we built this experience sampling application that you see here, and it would periodically interrupt users every about 7 to 15 minutes in a random interval, and then ask them after it kind of vibrated and woke up the screen, it said, what were your hands just doing? We sort of periodically interrupt them, find out what their hands are doing at that moment in time. And there was a big long list, and they could also type in their own things using a companion smartphone app. And so we had 50 users cumulatively wear a fleet of smartwatches over 100 deployment days, and we collected about 950 worn hours of data. And then we compiled all this data together to really figure out, not only for training, but also figure out what were hands doing. And actually, a vast majority of the time, you can see up here, hands were idle in something like a third of our data. So it actually turns out hands are still quite a bit. But nonetheless, there was a really, really long tail of really interesting actions. And from this, we picked out 25 that we thought were particularly interesting that future smart assistants might want to know. So here's that set of 25 and also the spectrograms. And you can see, they're not perfectly distinct, but this is sort of the power of deep learning is with enough training here, you can actually pick out some of these small differences and build a fairly robust model. So this is just a very quick, I'm not going to play through this whole thing, but this is the live classifier. In all of our projects, we always like to show the signals. Now, if it's a real thing, show the signals. If anyone who just shows you a machine learning result, I don't believe it. Show me the signals because I think that really makes it very honest, what's actually classifiable. Of course, there are exceptions where machine learning can pick up on things that even humans can't see, but in general, I think, to be honest with your signals. So you can see here, there's actually a little bit of flickering in terms of our class. It does get it wrong, and you'd have to, in a practical system, you'd want to do some sort of temporal voting scheme or something to stabilize that result. But overall, it actually works surprisingly well. And what I'm extra proud of in this project is that my student, Gerard Laput, who graduated last year, and he went off to Apple to start a research group, he was able to squeeze down this model and actually do the background hand washing feature that's now on all Apple watches to improve hygiene and, more importantly, to combat the spread of COVID-19. So if you have an Apple Watch, you should download the update and definitely turn that feature on. And it came from this exact clip that you're seeing right now. So we're running a little bit out of time, so I'm not going to go into any more projects on that end, but there's a bunch of other projects in this space that my lab has done. So if this is a topic that you're interested in, I would encourage you to look at my webpage, because we really do believe that context awareness is a key missing ingredient to really pull off this future. But I want to switch gears a little bit, give you a little bit of diversity in the sort of research topics that we're thinking about, and move away from input and actually towards a very complementary research thrust looking at pervasive output. And that's because if we want computers to be good partners, we not only need to think about ways for them to kind of draw in the environment, but we also need to think about ways to embody them in the environment so they can be that proactive partner. And in this case, I'll just show you very quickly one thread of research we've been working on, which is through universal kind of pervasive projection. So probably the best example of this research, and again, this is something that we've been working on for 5-10 years. But this is sort of the culmination of a lot of our efforts, which is this computer light bulb that we've been working on. It's roughly floodlight bulb size, and it does screw into most fixtures. It gets its power from that Edison screw fixture at the top there. And it's a totally self-contained computer. It has a computer, has a projector, has a depth camera, everything it needs. You just screw it in and it turns on automatically. And the idea here is that you can take one of these bulbs and unscrew your old, incandescent or maybe your LED bulb that you have in your desk and screw in one of our bulbs instead. Or maybe in a kitchen, you have recessed lighting, you unscrew a couple of those bulbs and again, screw in one of our bulbs or maybe even a few of our bulbs instead. And the idea is from these kind of advantageous viewpoints with good line of sight to work surfaces, office desks, kitchen countertops, is we can now project embedded interfaces. Now this case, we're just projecting the first step along this progression, which is a multi-touch interface. But this is basically sort of a iPad-like experience, but living on your world. But it can also snap onto real-world objects. It can actually evade objects. So obviously, if you launch that number keypad and then you put your coffee mug down onto it, you don't want it to start injecting spurious input into your spreadsheet. So it has to learn how to run away from cups, but sort of not run away from your hands. So lots of little individual challenges here. But we do think this is a very nice complement to having computers to sort of be draped in the experience. They know about your whole house and they sort of live in your whole house. But instead of having to, again, instrument every little facet with a computer, is we think projection is a really nice way to kind of drape interactivity at a wide scale, at a room scale, certainly. So, a lot of people are working hard on this vision. I think we can actually get to something in sort of the 2022 range that packs all the necessary ingredients together. And we've been hard at work teaming up with various OEMs to miniaturize the requisite components to pull this off. And this is 2 years ago, we actually teamed up with an OEM and we created the world's smallest projector computer. We actually kind of overshot our objective of putting it into a light bulb. When we finished with this kind of a collaboration, we said, well, this is so small, we can actually stick it on your body. And so we actually ended up making a smartwatch that allows us to appropriate the skin for, sort of like an extended interaction area. Obviously, you could still have a screen here, or maybe you could shrink this down into just a wristband and you don't need a screen at all. But the technology is certainly coming along really well. So just to kind of wrap up here, we're almost at the 30-minute mark. So let me get final thoughts here. Is I want to again kind of poke at this historical trend especially about knowledge in this case. So in the 1940s and 50s, computing was entirely limited to the information that was loaded into its memory, right? Like whatever the computer knew existed in its memory banks, whatever someone had brought in on punch cards or on tape reel. And it didn't know anything about the outside world. It had no connections to the outside world, knew nothing about the real world, really. And then as we move into the 60s and 70s, knowledge expands. So now we start to see, obviously larger hard drives and so on, but we start to see the emergence of proto-internets like ARPANET. And more importantly, we start to see very select live digitization of the real world. So systems like SAGE, which was a US strategic air defense system that obviously had to reach out into the world and integrate, geospatial radar data, weather data, location of planes, and so on, and have a digital, like a kind of a real world representation, but living in the computer. Now, it didn't really have context awareness, but it started to lay the grounds for having this fusion between the real world and the digital world. And then into the 80s and 90s, again, knowledge continues to expand. The World Wide Web emerges. Computers get access to this huge boost of knowledge, although it's largely unstructured text, which is still true today. But we start to see public web services doing things like weather reporting, and we eventually get to live traffic too. And again, weather and traffic are great examples of very specific and very high value facets of the real world that we want to digitize and bring into a computing experience. And so we tended to get those online earlier. And then, into the 2000s and really to the modern day is we've seen an explosion of IoT devices that are much more readily capturing the state of the world and making it available through, the internet, through wireless connectivity. So whether that be your house's, internal temperature or the status of some industrial machine, like never before, the state of the real world is becoming accessible to computers. And so if you kind of translate this into a trend, it probably looks something like this, that computers have been increasing their knowledge of the real world slowly but steadily over the past kind of half century or so. And that wealth of knowledge is accelerating. And that's really exciting. We're going to be at this sort of hockey stick moment where finally computers know what's really going on around them and they can proactively start to participate. So I think this means we're actually getting reasonably close to what might be described as sort of level 1 context awareness, where our smart devices can at least answer basic questions about their immediate environment. I mean, I think it's actually really sad today that if you ask, for example, a Google Assistant, is my laundry done? It says, I don't know what that is, but here are some search results on is your laundry done? I mean, seriously, we call these things smart devices. We're a long, long way away from that. But I think finally, the necessary kind of ingredients are coming together where we can start to practically enable this with a little bit more work. So maybe kind of in the 1 to 2 to 3 year time frame. And of course, there are some specialty applications like glass breaking that are already starting to creep onto these devices. And there's some new accessibility features in iOS that are also starting to listen out for things like doorbells and so on. So I think we're starting to get all the building blocks necessary to unlock these computing experiences where we're going to have computers that are much more like human assistants, or really much more like these coherent partners in our task in the future. So on that note, I'll finish, and we can save the kind of latter 25 minutes for questions.
Awesome, thank you. Awesome, can you hear me, Chris?
Yes, I can.
Awesome, thank you so much. This was fantastic. All right, so we have about 100 people actually watching, so I'm pretty sure you'll have questions for Chris. So I believe you can type them on the chat and we'll be able to see it. And in the meantime, I can start asking some questions just to fill in while you're all thinking and typing your questions into the chat box. So I actually, curiously enough, I found the result where you said, well, at the top of our results, the hands were idle was the most voted experience sampling moment. I thought that was super interesting because I feel like all the devices that we have a really hard time in figuring out what idle mode is, right? The constant false negatives and false positives because they simply don't understand what idle means. And I think there's lots of complexity in what we humans say when we say the hands are idle. Have you or Gerard now at Apple gone back to that data set and try to figure out if we could just get really good at detecting what idle means based on those results? Or are you guys thinking about that?
So we haven't really I'm sure Gerard has gone back to those results in his recent efforts at Apple. But I mean, idle, so this is user labeled data, right? So it's going to be always a little bit tough to interpret that. We didn't follow people around. That was sort of the point, is to sort of let them loose for 100 days and see what comes back. And, there was always the challenge of, badly labeled data and people dismissing it and so on. But generally what we saw is that idle doesn't mean still. It isn't that your hands are sort of frozen, but rather they're doing some like inactivity. They're just resting on your laps, or maybe you're fidgeting a little bit. You might be sort of, watching TV, and it's not that your hands are perfectly still, but that they're not engaged in a task is how we interpreted it. So we had a lot of accelerometer data, but we didn't, it was we had to do some of our guesses based on what people were doing. But that's what we saw in sort of post interviews and also, just piloting the application ourselves, is that, we would also label our hands as idle a vast majority of the time. Like, even though right now I might be, talking to you, is if my hands are like this and that buzzer goes off, what are my hands doing?
Exactly.
This is probably pretty idle. It's not like I'm preparing dinner or typing or something that's a very discrete activity. And then that was a major challenge. If you look through that paper, we had a big challenge, basically affinity diagramming. All of the people came up with crazy labels for like everything, right? And so what is swaying, or what is walk waving and stuff like that. So we had to kind of curate that to make sense of that data, and we did the best that we could.
I think that's super interesting. I think that those are some of the real challenges that are still necessary to put this out into the world. All right, we have already a bunch of questions coming in. I'll just read some of those as they come in. So Jasmine seems to be the first, and she's asking, hey, Chris, thank you for a great talk. I was wondering how you or your research group engages with some of the security concerns that come with IoT devices gaining more knowledge with power, as you were talking about in the closing statements, and how do you engage with the implications of that? And then there's a question, I think, that tackles onto that. I'll just ask it at the same time too. And sort of, how do you build systems that address some of those concerns? That's by Dasha, the subsequent question.
Yeah. So excellent question. And I'm glad that you brought this up. And you're absolutely right. As there's basically this axis, right? That as sensing becomes higher fidelity, knows more about you, it has more power, it has the ability to proactively intervene for good or bad in your life, then obviously that invasiveness of that sensing has to go up in a corresponding way. And if you plot kind of most sensors, they end up along that diagonal. This is something that one of my students right now, Corona Huja, is thinking really deeply about. So you have, something like a barometer or temperature sensor. It doesn't know who you are or what's going on in the room. It can sense something that's very specific, but not very privacy invading, all the way up to like a camera, which knows who you are, what your facial expression is, who you're with, what you're wearing, everything, right? And so most things lie along this diagonal axis. And it's starting to become really interesting to think about in HCI, how you pull off that axis, how you have something that's kind of low invasiveness while also high fidelity. And we don't really have great models for how to think about that. And so, the kind of immediate solution, to give you a little bit of something tangible to think about, is we always believe in doing edge processing. So for like the Apple Watch doing this hand wash detection, that isn't just shipping, data back to the cloud to Apple, every 1 second, eating up all your batteries as well, is it's doing it all locally. And I really do strongly believe that edge processing is the way to go. And actually I have a startup company that is one of the leaders in basically doing machine learning for edge processing and deploying it to very small, $1 microcontrollers. How do you do that effectively? How do you do advanced machine learning techniques on a processor that costs $1? And so I actually don't believe in really the IoT. I believe sort of in just the T part. I think we want machine learning on things, but I think it's kind of a lazy crutch by industry, or maybe kind of a sneaky ploy to get all of our data to have to ship everything to the internet. And I always find, people make fun of, like the internet connected toaster, or like, why does a toaster, need IoT? Why does it need machine learning? And at first glance, you're like, that's ridiculous. Like an internet connected toaster. I mean, what are you gonna do? Put in toast, like put in bread before you go to bed, and then when you wake up, you ask Alexa like make your toast the next day. It's one of those things that's almost become a meme in sort of the IoT community. And I think that actually misses the larger point, which is that consumers actually do want a smarter toaster, right? Our notion of a smart toaster right now is that it's like Wi-Fi connected and it talks to you. But actually, I think a smart toaster is one with machine learning built in. It doesn't need internet connectivity. I don't mind paying $5 more for a toaster that employs machine learning and a microcontroller to make better toast, tastier toast that's fast, and makes it faster. That's a great use of edge machine learning that I don't need an internet connection for. So I think we need to move away from just sort of the blanket, let's ship it to the cloud mentality and go to a much more privacy preserving and security preserving edge ML kind of model. So hopefully that answers a little bit of your question. It's a big topic, so.
It's a big topic, but I think it totally does. It's focusing on the functionality that it offers rather than the connectivity, which in a lot of the cases is actually superficial. I really like that take on it too. The next question is from Yuji Tao, who's also an HCI student. And Yuji's saying, thanks for the talk. Most of the work is based on devices such as laptop and watches. And I think Yuji's mentioning this as in the user glances at those devices to get output. I'm interpreting here. Have you looked at other computing devices that might have better fit the context? And she says, not everyone might be looking at their laptop nearby while cooking. So I think this tackles to the output part of your lecture as well at the end of it.
Yeah, I mean, so the lab does a lot of things, and my students are, very talented set of folks, and so it's hard to capture everything and hard to put it into a presentation. But yeah, we think a lot about the output. How do you embody this? How do you distribute this computation and interactivity across an environment? So yeah, you've deployed all these sensors, but then what do you kind of do with it? And how do you embody that and expose that computation? And so obviously at the very end of my presentation, I talked about sort of projection light bulbs that, hopefully one day you'll be able to go to Home Depot and buy a 6-pack of these bulbs and then go replace them in strategic locations in your house and have an interactive coffee table, an interactive, dinner table, interactive wall that for the most part can just emit light. I mean, the funny thing is that the killer app of light bulbs is light. And that's still going to be true for this kind of interactive light bulb as well. And sort of when you make a gesture or speak a command, the light can transform into something that is digitally malleable. Another example of a project we did, I think we published this maybe last Chi or maybe the Chi before, is this idea of digital ventriloquism. So we use these very unusual speakers called parametric speakers. They're sort of what might be described as a sound laser. And we can actually produce ventriloquistic effects where any part of your room can sound like it's talking to you. So a plant can talk to you and say, you haven't watered me in a week. The plant is just a plant. There's no electronics or anything special in the plant, but we can put all the kind of clever stuff, all this clever beamforming technology in something like an Apple HomePod, and yet have your plant be the embodied agent that speaks to you, perhaps in its own voice, whatever you want to do, and actually be able to embody that information and that power where it's contextually relevant. That's another audio-only way to do that. And of course, with a smart speaker, it's kind of weird if your Alexa's telling you that the plant is, needs water, then it has to name the plant and where that plant is. And it's actually a much more complicated computer vision problem and so on. And so actually it's kind of nice to have it embodied at the plant. But again, make it practical. We don't want to have to put microphones and speakers and batteries on every single object that might want to talk to you in a house. That becomes $1 million house and no one's going to want to upgrade.
Well, what's next? This is my question now, but I was just curious when you showed the light bulb. What's next on that side is the question now purely mechanical, as in what are the next steps to roll this out as a commercial device, or are there challenges that you think HCI students out there, not just at U Chicago, should be working on, things that you consistently stumble upon when you and your students are working on the smart bulb idea? What do we need to pass the state of the art?
Yeah, I mean, it is getting pretty close to, where researchers have to sort of let go a little bit and let industry and kind of economies of scale and so on bring it to the next level. I mean, the light bulb that I showed you was like $2,000. No one's going to go buy a 6-pack of those, at Home Depot, right? And so we need to get it down to like $300 or $200 or $100 to really, so it's a mass market kind of thing. So that's going to hold it back, and that's what industry does really good at. But a really thorny problem, projectors are pretty good. We pretty much solved projectors. Projectors have been around for like 30 years. They're fine. The hard part is actually touch sensing in an ad hoc way. You want it to work on your IKEA table, but you don't want to have to change your table. You don't have to replace all the furniture in your house. And so how you do touch tracking with computer vision or depth cameras or some other kind of complicated scheme is still very much an open problem. I will put out the post for you guys to think about. I believe the farthest range someone has demonstrated finger touch tracking, so you can poke with a finger on a button on an ad hoc surface, is 1.6 meters. This is one of my own papers, so I can make fun of it. 1.6 meters is pretty sad. It's pretty pathetic. That's going to be a light bulb immediately above your desk, maybe above your countertop. It's not going to work across the room. So there's a real challenge, and how do you get that up to something like 5 meters so you can have pervasive touch interaction everywhere? Big problem. We can project anywhere. That's sort of solved, but we don't have a great way to do touch tracking everywhere.
Question is out there. Challenge for the students. Actually, let me tackle on some of the things you're saying, because I have one interesting question here from Shan Lu. She's faculty in our department, and Shan is asking via YouTube. She's asking, other than sound, what are other helpful signals for identifying users and their context?
So, as I mentioned in synthetic sensors, the very first paper that I went through is we actually do an information power analysis of all the different, I think we had 16 or something sensor channels on our board: barometer, temperature, infrared, thermal, sound, vibration, electromagnetic radiation, and all those kind of things. And when we rank order those, you'll see that sound is number one, followed pretty closely behind by vibration, which is why we decided to pursue it in other projects. Then it's a really sharp drop off. But what you find is the other modalities, the other sensing modalities, are really useful for edge cases, like to know if a kettle is getting warm or if a gas stove is on. You really need something in the thermal channel. Sometimes the sparker, right, when you turn on a gas stove, that can be sensed with electromagnetic sensing, sort of like Msense. But if it's like just if once it's on, to know if it's on or off is really hard. It's really more of a thermal output. But in that paper, we tried to take a first stab at codifying the relative power and relative utility of those different modalities. But at least in our initial stab at this problem, sound and vibration, especially when put together, are really powerful. And we do have a follow-on paper, which I didn't talk about, which is talking about how if you have one sensor per room, how, let's say you have 10 rooms in your house or something on that order, how do all those sensors work together? Because it actually turns out that, when you flush a toilet in one room, the microphone in that room can hear it, but the room below it actually picks up the vibrations of the plumbing. And how do they all work together to enable really high accuracy, result with, no false positives? And so there's a paper on that as well that you can dig up.
That sparse sensing idea is really cool. In fact, there's a bunch of questions from students and faculty. For instance, Heather is asking lots of examples for indoor environments on single user operations for tracking, especially with sound. Any thoughts on outdoor or multi-user operations where many sounds actions are being put together? And Sheena Liu is asking a similar question, saying, what are the general ways you get rid of unexpected or simultaneous noises with these approaches?
Yeah, awesome questions. Simultaneous detection with sound is a really huge problem. We've looked at it. We've sort of given up, quite honestly, for a little bit. There are other more kind of acoustic-based researchers. Again, we're kind of generalists in my lab, but there's certainly people that are real experts in acoustics that are trying to do multi-sound source separation and so on to try to tease apart that problem. And once we kind of have that core technology, then we might go back in and see if we can enable it. But right now, we have very much hit sort of an immediate wall in terms of dealing with it. And that's not unique to computers. I mean, if if it's like Thanksgiving with like my parents, it's like someone's like vacuuming and there's like dishes going on, there's music, there's like a kid screaming, there's a dog barking, even humans are going to have trouble picking up, especially a very not very noisy event that's going to be happening. That's just inherent to kind of, signal to noise ratio. And in our system, if you look through the whole video of like synthetic sensors, we do show a bunch of event simultaneous detections, but they tend to be in different channels. So if you have sort of your stove running and your faucet running, those get kind of tickle the sensor in two totally different dimensions, and therefore you can reliably detect them. The classifiers are sort of tuned to their own respective channels. To the second half of your question about outdoor sensing, we thought about this too, and actually we just submitted a paper to Kai that is, instead of, we tried to, Yang Zhang, my student who's just graduating, he kind of went from kind of one-to-one, like basically building sensors to make smart objects. Then he started to explore a lot of the room scale sensing, like synthetic sensors. And then now he's trying to say, well, instead of just having one per room, can you have one sensor per building, or even maybe just one sensor per city? What does that even mean? What could that possibly be? It sounds like science fiction. But he actually did send in a paper to Kai called City Scale Sensing, and he's uniquely doing it with long-range laser vibrometry, which is a very cool technology, and he built his own version of it, and we're able to actually sense up to about 1 kilometer. And now so basically, if you get up really tall, so there's some great, tall buildings in Pittsburgh, same in Chicago, you could go up, to the top of Willis Tower, set up this rig, and you could probably get, with a professional unit, let's say we get to like 2 kilometer kind of range, you could probably sense something on the order of 1 million different facets, every stop sign, every road marker, every parking spot kind of deal, everything obviously within line of sight.
And you're saying sensing, like, is there a car in the parking spot, or is there a type of activity in the parking spot?
So we can do presence. So like, is there a dumpster here? Is there trash full? Is there a parking here? And we can also actually register the vibration. So what he shows is that you can pretty much turn all retroreflective surfaces. So that's like license plates, street signs, parking signs, bus stops, like pretty much the cities have already deployed these by the tens of thousands. You can basically turn them into remote accelerometers for free. So cities have actually already paid to deploy all this infrastructure. And that's sort of the core essence of our Kai paper.
Very cool. I'm going to
then I can share with you guys.
Awesome. I'm going to transform this question from Tsu Cheng Ku into my own version of it as well, because I think it's a very cool question that they're asking. He's saying, in your presentation, it seems like you're leveraging the different signals to understand the first order, building up to second order, and et cetera. What would mean to have computers, and especially these small sensors, edge computing, small devices, to get to the nth order, like our cognitive level of understanding? What is missing to get all the way up there? Is it a software problem? Is it a hardware problem? Is it multimodal sparse sensing? What's your thoughts on that?
Yeah, also a really excellent question. So I actually don't know fully. So you can sort of see I kind of mumbled off on that slide, like, oh, whatever, nth order, kind of waved my hands and moved on to another project. And that's because it does get murky as you go up. Like we know we can build, okay, we saw that, the microwave went on and then this happened and so on. And we can sort of start to build up this big model. There's actually a really cute example. I should have included it in the slide deck, but we had data from someone's home and they allowed us to basically analyze. And then we actually followed up with them. We saw this really weird and very interesting patterns of events. Like we saw, the lights come on in the house. Then we saw those sort of electromagnetic radiation that was impacting the Wi-Fi, signal strength rather, or SSI. And then we saw kind of a raise in humidity in the environment. And then we saw that Wi-Fi kind of dipped again. And we saw this we had a light sensor, color light sensor. We could see the lights were all changing colors. And we're like, this is a really weird back-to-back sequence of events. And what was this person doing? So we went back and said, like, what were we doing like Thursday night? And they're like, oh, I think I came home. And it turned out what they'd done is they'd come on, flipped on their lights, went to their kitchen, put ramen in the microwave. So that microwave was actually what was causing our SSI drop on the Wi-Fi. Then when they opened the door, this kind of plume of humidity came out that actually spiked the humidity in their kitchen. And then they came out and watched Netflix, which is why, again, our Wi-Fi strength went down. Those basically packet collisions. And the kind of dappling of colors was because the TV was basically changing the color of light in the room. And it's one of those cases where we kind of, after we looked at it, we said, we're never going to be able to codify all the rules for someone's watching Netflix eating ramen, like that. There's so many combinations. It's basically impossible to do it combinatorically. And that's when it really kind of became clear to us that you can only go so far with these rules. Like, sure, it's nice to have the microwave made ramen sensor, a microwave made some sort of liquid bowl sensor. But then after that, it starts getting kind of decreasing in utility because it just starts to spread into too many avenues. And that's where it's going to be sort of natural language processing, not natural language processing, but sort of like understanding and sort of semantic web and all these kind of old topics are going to have to come back to rescue us, to kind of pack down again that complexity so that we can build things back on top of it. And it's very much an open question, but we can definitely move. We know I think there's undisputed utility moving from, faucet is on or off, or a laundry machine is on and off, to start at least building some primitive things like they're doing their laundry, or, they've used 3 gallons in the last minute and it's like an on-off sequence that's more indicative of, washing dishes or, getting a drink than it is like whatever, making tea or something like that. But there is going to be this point where we're kind of too clever for own good, and we're going to have to go to something like deep learning techniques to really take us the rest of the way.
But what I also liked, maybe this is part of the answer to Chu Sheng's question, is that when you show that project, I forget the name because it's one of the new ones, where you stop the user and say, what was that? And the user labels it. That was my microwave, by the way. I think that's kind of where it has to head in terms of these super complex multimodal machine learning approaches, right? Where there's absolutely no way you're going to make sense of it based on the crude individual outputs. You're not going to be able to combinatorially understand what's going on. You just have to ask a human that made sense of it because they have agency and they know exactly what was going on, right? So I really like that. And in fact, I was wondering if you wanted to comment on that, because I love that project, but I feel like if you would roll that out tomorrow, people would want it to work on the first minute rather than on the 30th interaction, right? So you collect a little bit of data, and then at the 30th interaction or so, you say, hey, what was that? And I'm wondering, is there a way to flip the whole script and we can get the person to label it first and then it works even if it's so-so?
Yeah, and so we do explore very briefly in that paper other strategies for eliciting essentially answers from people. And we can also shift how aggressive or conservative we are on when we ask. Like, do you only prompt them when you have, your 100 hours of faucet data? You're only going to ask that one time. It has to be 100% correct. Or, after 10 minutes of unboxing, the very first time you hear a faucet, you can say, like, sort of like a baby, what does that sound? Or like a child? What does that sound? What is that thing? And they're just needling you with questions all the time. And you can sort of dial that any way you want. And of course, we can bootstrap it. We don't have to be totally naive. We can bootstrap it with a plausible, what we already sort of know that faucets sound different from microwave beeps, right? Actually, beeps turn out to be a separate class in our data sets. And also, we found that if you elicit the answer in different ways, so not just saying, is that a faucet? You can say, what is that? Or you can say, was that a faucet? And sometimes even what we found is when it got it wrong, like, no, that's not a faucet. It's a whatever, blender. Right, is that actually it starts to kind of anthropomorphize it. And what you saw people doing is being much more forgiving, because they actually likened it, even in the interview quotes we collected, they likened it to teaching more of a child. And they were much more forgiving when it made mistakes versus, it's supposed to be this robust out of the box experience. And when it gets it wrong, you're like, oh, this thing is so frustrating because, it's getting it all wrong. When you've sort of taught this thing yourself and you can even feed it more data, hey, what I did was just a faucet, or it interrupts you for the 5th time. Is that still a faucet, or is that something different? You actually give it a kind of lot more social grace to learn. But those are very preliminary results, and there's a little bit talked about in the paper about that. So certainly a very interesting topic for future work if someone's interested in that.
That is super cool. I just realized we're over time, so I'm going to choose one last question that is more high level, so we can finish on a high level note, and then I'll pass all these questions that are still coming in. I just saw 3 more come in to Chris. Maybe there's a way that we can tackle them offline, especially for the folks that I do have the email. And I'll ask a hybrid of Jesse's question. Jesse's a student of UChicago that just went to UW, and Sarah Sebo, who you met today. She's one of our new faculty in our department. So both of them, I think, are asking, this work is super cool. What do you think are the new applications to this? Jesse, for instance, asks, do you think there's sound-based activity recognition that we can use for sake of accessibility? And Sarah is asking, of all the things that you're seeing in your work, what are the information that the devices, once they gather, can completely change our everyday life, right? Like the most impactful information that could really change the way we interact once these things become context-aware. So I leave it to you.
Yeah, wow, you guys don't ask simple questions, huh? So, I think, the kind of the base kind of questions, okay, like these kind of questions are the first step. They're kind of the baby step towards that future. And I think there is utility in this. I would love to know. I'd love to be able to say, is my laundry done? So I can know and go up and put it in the dryer, or whether or not I have like an Amazon package waiting outside for me because the person didn't ring my bell during the pandemic, et cetera. Right. So like even just some very primitive basic knowledge that, again, if I had a in-person human assistant that just like lived in my house, they would be doing these things kind of automatically for me. So I do think this is very much a baby step towards that coherent partner that kind of the folks that worked on Sketchpad, and also mirrored by Licklider and Engelbart and Vannevar Bush and all those people. Right, this is a very well defined long-standing vision in computer science. So I think to get to that coherent partner where we don't use not just computers as tools as we see them today, but really that they are standing alongside you. They kind of bring their own tools. You bring your tools, they bring your tools. Now we have this sort of like mesh up of tools, and we're each good at our different things. Computers are obviously fantastic at doing things like drawing parallel lines and instantly dropping in all the resistor values to make your circuit safe. And I'm the one who's creatively designing some new sort of filter to remove noise from LED bulbs and so on. And so I think like that kind of agent that kind of sits alongside you, kind of a plus version of Siri, is where we want to go. I don't know if there's a single killer app there, but I would think you can think of the killer app as analogous to having what a human assistant would be like today. So in some respects, and I agree it's a little bit maybe dystopian, but if you want to envision sort of what the future of autonomous cars is, where you can have an autonomous taxi, you can sort of just envision that through the pervasiveness of Uber, or at least pre-pandemic Uber. And I think you can sort of use a similar proxy, which is, what's the future of these really deeply personal assistants? And I think you can sort of imagine, what would it be like to have a human assistant that's awake 24 hours a day, that's just following me around and intimately knows my schedule and my preferences and the state of my house. they would be even better than human assistants because they can obviously tap into the whole, knowledge of the entire World Wide Web. They can tell you everything about the whole planet, essentially. And I think obviously, this is almost a science fiction notion, but I think we'd all agree that would have incredible potential to reduce our, workload, make our work better, be able to spend time more proactively with our family and friends and be better humans in general. So yeah, it's a big vision. We're decades, if not centuries away from achieving that, but I think it's important to get the building blocks in place and build up.
Fantastic. I love ending on that note. All right. I want to thank you once more, Chris, for your time and for coming over to our inaugural session of the Distinguished Speaker Series. I'm just going to project the slides once more so I can invite you all to join us for the subsequent talks that we're having in the series. Chris was the first speaker. I was really, really happy and thrilled to have him over. He's going to meet with some of our students now, which is even better. But we have Anand, Carrie, Tanzeen, Amy, and Hiroshi still coming all in this fall. And I really hope all of you can join us. And in fact, Anand is just next week. So feel free to join us. It's the same YouTube channel. And we'll send out a registration link if you want to join us on Zoom, like the 50 folks that joined us today. Thank you so much, everyone. And thank you, Chris, once more. Bye, everyone.